In this module, we will explore reversible reactions and their significance in chemical kinetics. In many kinetics studies, the focus is on irreversible reactions far from equilibrium, where the concentration of products is low and the reversible reaction is often negligible. The kinetics of such processes is often described by simple rate laws, which we have discussed previously. However, as a reaction progresses and a system nears equilibrium, the concentration of products increases, making the reverse reaction increasingly significant. To accurately describe the dynamics of a chemical reaction, especially as the system approaches equilibrium, it's necessary to consider both the forward and reverse processes. This schematic representation of a chemical reaction, employing the concept of a reaction coordinate, helps in visualizing this process. It illustrates that reactants can form products if they possess enough energy to overcome the activation energy barrier. Similarly, from the product's perspective, they can revert to reactants by overcoming a corresponding activation energy barrier. In this module, we will discuss the kinetics of these reversible reactions. Reversible reactions are those where the conversion of reactants to products and the reverse process, the conversion of products back to reactants, both occur. This dual nature of reactions is crucial for understanding how chemical systems reach equilibrium. Reversible reactions discussed in this module also serve as a first example of complex reactions that we encounter in our study of chemical kinetics. A reaction scheme is a way to represent the sequence of steps of a complex chemical reaction, including both forward and reverse processes. It illustrates the reaction mechanisms of complex reactions. Let's consider a specific example of a reversible reaction where both the forward and reverse reactions are first order. It will also illustrate the usage of reaction schemes. The reaction scheme of this reversible reaction can be represented by the following set of chemical equations. The forward reaction involves the transformation of reactant A into product B. This reaction is first order with respect to A, and its rate is governed by the rate constant Ka. It is represented by this equation. The reverse reaction is the conversion of B back into A. This is also a first-order reaction, but with respect to B, and it is characterized by the rate constant Kb. It is represented by the equation shown here. By combining these two reactions, we can represent the overall reversible reaction by this reaction scheme. It is an example that sets the stage for further exploration of more complex reaction mechanisms in chemical kinetics. In this reaction scheme for a reversible reaction, Ka is the rate constant for the forward reaction of A to B, and Kb is the rate constant for the reverse reaction of B to A. These rate constants are essential in determining the dynamics of the reaction, including how quickly the system approaches equilibrium and the composition of the reaction mixture at equilibrium. For a reversible reaction represented by this reaction scheme, the integrated rate law expressions can be derived from the differential rate expressions for both the reactant A and the product B. For reactant A, the rate of change in its concentration over time is given by minus Ka times the concentration of A plus Kb times the concentration of B. This equation indicates that the concentration of A decreases due to the forward reaction at a rate Ka times the concentration of A, but it also increases due to the reverse reaction at a rate Kb times the concentration of B. The first term is the same as in a first-order decay reaction, but an additional term is included to account for the formation of the reactant from the decay of the product. This duality in the rate expressions reflects the reversible nature of the reaction, where both formation and decay processes are continuously occurring and influencing the concentrations of A and B. For product B, the rate of change in its concentration over time is Ka times the concentration of A minus Kb times the concentration of B. The concentration of B increases due to the forward reaction and decreases due to the reverse reaction, each at rates equal to their respective rate constants and the concentrations of A and B. In the special case where only the reactant A is present at the beginning of the reaction, T equals 0, we can apply specific initial conditions to our reversible reaction model. This scenario is common in kinetic studies and provides a clear-cut illustration of how the concentrations of reactants and products evolve over time. If the initial concentration of A is denoted as concentration of A0, then for any time t, the sum of the concentrations of A and B must equal the initial concentration of A. With these initial conditions, we can integrate our rate equations to find the concentrations of A and B at any time t. The resulting equations are presented here. They show how the concentrations of A and B change over time in a system where initially only A is present when a reversible reaction takes place. This figure shows the time-dependent behavior of reactants and products concentration as predicted by the equations. Initially, the concentration of A decreases over time, exhibiting an exponential decay. This decay is governed by an apparent rate constant, which is the sum of the forward and reverse rate constants. On the other hand, the concentration of B increases exponentially, following the same rate constant. In the absence of a reverse reaction, we would expect the concentration of A to eventually reach 0. However, the presence of the reverse reaction changes the outcome. Instead of completely depleting, A reaches a non-zero concentration at equilibrium. Similarly, B grows to a certain level and then stabilizes. Theoretically, equilibrium is reached after an infinite amount of time. Practically, equilibrium is considered achieved when the concentrations of reactants and products are sufficiently close to their equilibrium values and their further changes are negligible. This state is effectively considered as equilibrium in experiments and real-world applications. The equilibrium state is established when the concentrations of reactants and products no longer change with time and reach their equilibrium values. Mathematically, the equilibrium concentrations of reactants and products are the limits of their respective concentrations as time approaches infinity. In our example of the reversible reaction between A and B, the equilibrium concentrations can be expressed by these equations. These equilibrium concentrations are proportional to the initial concentration of A and are influenced by the rate constants of the forward and reverse reactions. The relative magnitude of the forward and reverse rate constants determine the ratio at which A and B will be present at equilibrium. At equilibrium in a reversible reaction, the concentrations of reactants and products become constant over time. This constancy is often misunderstood. It doesn't mean that the reactions stop. Instead, it indicates that the rates of the forward and reverse reactions are equal, maintaining a dynamic balance. This equilibrium state is characterized by this equation. This equation demonstrates that at equilibrium, the rate at which A converts to B and B converts back to A are the same, leading to stable concentrations of both A and B. By analyzing the differential rate expressions for reactants and products at the equilibrium state, we derive the following equation. Here, Kc represents the equilibrium constant in terms of concentrations. This equation is significant as it links the kinetic and thermodynamic perspectives of a chemical reaction. It shows that the equilibrium constant Kc is equal to the ratio of the forward and backward rate constants. The larger the forward rate constant compared to the reverse one, the more the equilibrium is shifted towards the products. This equation elegantly connects dynamic reaction rates with the static chemical equilibrium. When considering reversible reactions with different orders for the forward and reverse processes, the kinetic condition of equilibrium still holds, but it requires a more nuanced understanding. Let's take the example of a reaction where the forward reaction is second order and the reverse reaction is first order. In such a case, the rate of the forward reaction is proportional to the product of the concentrations of A and B, while the rate of the reverse reaction is proportional to the concentration of C alone. Here, Kf and Kr are the rate constants for the forward and reverse reactions respectively. The equilibrium condition is achieved when the rate of the forward reaction equals the rate of the reverse reaction. At equilibrium, rearranging this equation gives us the equilibrium constant Kc in terms of concentrations. This equation shows that even when the forward and reverse reactions have different orders, the equilibrium constant is still defined by the ratio of the rate constants. It underscores the circumstance that at equilibrium, the rates of the forward and reverse reactions are equal, leading to a constant ratio of product and reaction concentrations defined via the ratio of the rate constants.